Hello everyone, welcome to this NPTEL course on computational process design. So in the today's session what we are going to look at is we are going to look at economic evaluation of the process plant. In the last session we have seen the cost evaluation of different equipments. So economic evaluation is a critical process primarily because we wanted to know what is the cost of the process plant, whether it is viable or not, what will be the revenue coming in, whether it is going to be profitable or not. So all these calculations are required to be done, and these calculations are not simple because there is also associated with this calculation is a time value of the money. So all these intricate factors play a important role in deciding the viability of the process plant. So economic evaluation, when we see, is a critical process used to assess the financial viability and feasibility of the projects, investments and processes. So economic evaluation begins with the thorough examination of both capital and operating expenses associated with the project or investment. So here you can see that the capital investments are something which you are doing in the starting of the project, and once the project is starting there is a operating cost involved. This involves breaking down cost into various categories such as initial investment, labor, materials, overhead, and ongoing operational expenses. So these include the total uh, uh, expenses. Those are evaluated in the economic evaluation. So in addition to the cost analysis, economic evaluation entails forecasting potential revenue. So this is very important. Forecasting potential revenues means how much money we are going to get from the particular project or investment, and this involves estimating sales revenues from service rendered or any other income streams associated with the endeavor. So you can see that this revenue forecasting is extremely important primarily because uh, in order to determine the income potential of the project and its ability to generate the returns, we need to look at the forecasting potential revenues of the given process plant. So key component in economic evaluation includes assessing capital and operating expenses, calculating profitability measures, and considering the time value of the money. So this is also important. So you can see that over the period the value of the money changes because of inflation, because of interest rate and other things. So time value of the money is also important, and also we wanted to assess the capital and operating expenses. Okay, so if you look at the cost associated with the economic evaluation, this can be divided into different types. So there is a fixed cost. So fixed cost includes the direct investment, overhead and management cost related to the project. Capital investment cost crucial at the project outset fall under this category. So you can see that the fixed cost is primarily nothing but the capital cost which we are doing it in the starting of the uh, project. Then the next part is a variable cost. So this category includes the raw material cost, labor cost, utility cost and other expenses, and these are actually related with the operation of the process. So in this particularly we are interested in looking at the manufacturing cost. What is the cost for manufacturing a particular product? Also the ongoing expenses incurred annually. Okay, so by conducting the economic evaluation, the organizations can optimize resource utilization, minimize risk and maximize returns on the investment. So you can see that the economic evaluation of the project is extremely important because the industries or the organizations wanted to see whether the particular project is going to use the resources optimally, there are less number of risk involved, or whether it is going to give you the maximum return or not. So all these aspects we can look at only by doing the economic evaluation. So capital investment in the context of economic evaluation refers to the initial expenses incurred at the beginning of the plant's life to build and start up the process. So these are the investment which we are doing in the starting of the project. So these investments are crucial for establishing the infrastructure and operational capabilities of the chemical process. The total capital investment comprises of the fixed capital and working capital components. So in this case, you can see that even in the capital investment, there are two types: fixed capital investment as well as the working capital investment, and we will see each of these. When we talk about the fixed capital investment, these actually represent cost of constructing the physical process. It also includes the equipment cost and facilities, and the cost related with the infrastructure necessary for the operation. So these are included in the fixed capital cost. So within again the fixed capital, manufacturing capital cost includes bare module cost. So bare module cost is nothing but what? This is nothing but the equipment cost along with the contingency factor, typically around 25%. So these are nothing but the equipment cost, and we again keep the contingency factor of 25% to account the unforeseen expenses. So this uh, bare module cost is included in the manufacturing capital cost. When we talk about the non-manufacturing capital cost, it includes the cost with respect to the construction of buildings. These are with respect to the cost of services, land, and other non-equipment aspects of the project. And typically, these are estimated as 40% of the BMC. So BMC is nothing but bare module cost. So we first calculate the bare module cost. We take the 25% additional contingency factor while calculating this bare module cost. Once we get the bare module cost, from that we can again calculate the non-manufacturing capital cost, which are nothing but around 40% of the BMC. Now this was with respect to the fixed capital cost. When we talk about the working capital cost involves the funds required to operate the plant efficiently. These accounting for the delays in payments, inventory maintenance, and other operational expenses. So you can see that typically the working capital components may include raw material and product inventories, goods in the process, and accounts receivable to manage cash flow fluctuations. So whatever the cash flow fluctuations are occurring in the industry, that are accounted through the working capital. So working capital will be nothing but some fixed amount of money is reserved for the working capital, and through that all these different um, cost factors are accounted. So working capital is replenished as additional revenue are generated. So you can see that as soon as the revenues are generated, this working capital is regularly replenished, so ensuring the availability of the funds for ongoing operations, so that you can have the sufficient funds for the ongoing operation. So typical range for working capital as a percentage of the total investment. So you can see that the working capital usually taken as a percentage of the total investment. A typical range which is used is around 10% to 20%. So between 10% to 20% of the uh, total investment is taken as a working capital. Again, this depends on project to project. So another guideline which is given by Douglas is, he has given a simplified formula for calculating the working capital. So he is suggesting to use 50% of the total investment as a working capital, or 19.4% of the fixed investment. So based on this we can directly calculate the working capital, and this is easy to calculate, and therefore this guideline which is given by the Douglas is extremely important while financial planning in chemical engineering projects. Now let's look at the manufacturing cost. This basically includes the expenses incurred on a continuous basis throughout the operational life of the chemical plant. So now we are talking about the operational cost associated with the project. So far we were looking at the fixed cost or a capital cost associated with the project, and now we are looking at the operating cost. So this basically involves the manufacturing cost. So these costs are directly related to the day-to-day operation of the plant and include both direct and indirect expenses. So you can see that when we look at the direct expenses are nothing but what? These are nothing but the costs related with the purchase of raw materials. These are the costs related with the labor, utilities, maintenance, and other operational expenses directly tied to the production. So whatever directly involved in the production, whatever the costs are directly involved with the production, all these costs are associated with the direct expenses in the manufacturing cost. When we talk about the indirect expenses are nothing but taxes. So whatever the taxes the plant has to pay to the government, insurance premiums, and also during the period, during the operation, there is a depreciation of the plant is taking place. So these taxes, insurance, and depreciation, all these are included in the indirect expenses. So they, if you look at even these indirect expenses, these also contribute in the overall cost of the production. Okay, so typical classification of the manufacturing cost, if you look at, so raw material cost is the major cost. So these constitute the feedstocks required for the process and are continuously consumed. So you can see that whatever the raw materials are purchased, that cost is included in the raw material cost. Then the second classification is a credits. So credits basically includes the usable purge gases, utilities such as steam and electricity, and byproducts generated continuously. So that's why this is referred as credits. So these are the purge gases which are used as a fuel, which are generated, also utilities like steam which are generated, and the byproducts generated. Then the next classification is a direct expenses. So direct expenses, if you look at, this includes the various costs such as labor, supervision, uh, payroll. Typically the payroll is taken as around 20% of the labor and supervision cost. Then the utilities like electricity, steam, and uh, cooling water and maintenance. Supplies, if you look at the supplies, that is around 2% of the fixed investment. And the royalties, usually if we are taking any licensed product, in that case we have to pay the royalties to the original companies. So uh, these are used whenever we are using some specific catalyst or some specific process. So in addition to the direct expenses, then there are indirect expenses. So indirect expenses includes depreciation. So typically the depreciation of the plant is taken as around 8% per year. Then there are local taxes and insurance. Typically local taxes and insurance are taken around 3% per year. So if you look at the depreciation expenses, these accounts for the gradual reduction in the value of the capital assets over time, and are typically calculated based on the useful life of the equipment or facility. So what we are saying is, over the use of the plant, you can see that these plant equipments erode, they are their wear and tear is taking place, and because of that we have to include the cost associated with that, and this cost we call it as a depreciation. So for example, if we are taking, let's say, $20,000 car, if you have taken an example, and if it is, we are saying that it is depreciating at a rate of 8% annually. So in that case, after 3 years, the value of the car will be what? It will be 15,200. You can see that 20,000 minus 20,000 into 0.08 into 3. So this will be nothing but the cost incurred because of the depreciation, and if we subtract that from the original cost of the car, so the new uh, cost of the car after 3 years will be 15,200. So you can see that this expense isn't directly incurred and is more of a theoretical cost, since it is not paid or received by anyone. However, this is a very important, because when you are calculating the depreciation cost, you know this have lot of impact on calculating the revenue and all, because the depreciation amount, you can claim the tax relaxation on the depreciation. Okay, so it is factored into certain economic metrics for comparative assessments. Then the next indirect costs are taxes and insurance expenses. These are included in manufacturing costs to account for the regulatory obligations and also for risk management measures associated with the operating the plant. So in this case, you can see that the insurance charges we have to pay in case some accidents are there. These charges should be covered through the insurance. So clearly the risk management is also associated with this, and in order to manage the risk, the insurance and other um, uh, costs are also included. So the total manufacturing cost is the sum of all direct and indirect expenses incurred in the production process. providing a comprehensive overview of the financial outlay required for the plant operation. So when we sum up direct and indirect cost, that gives us the total manufacturing cost. This total manufacturing cost, and this is the operating cost. Similarly, we can calculate the total capital cost, which is the fixed capital cost and working capital cost. That will give the total capital cost, and both capital cost and the operating cost, that total is going to give us the total cost of the project. Now let us look at some of the terminologies which we are going to define here, because these are important when we are designing a complete plant. So simple measure in economic evaluation provide a quick assessment of the process profitability, but may have limitations that need to be considered cautiously. So when we are just calculating the cost and profit, and then based on that if you are making the decision, that is very easy to do it, but such decision making has some limitations, and we will look at what are such limitations as we go ahead. So these measures offer a preliminary understanding of the financial viability of the project. So clearly such simple calculations can give you the preliminary understanding whether a particular project is going to be financial viable or not. Okay, but more detailed calculations are required in order to get the exact numbers. So clearly such simple calculations of a project may not capture the full complexity of the cash flow and timing consideration. So you can see that here when we are calculating the gross profit based on the cost and the total revenue, it does not say anything about how the time value of the money is changing, and it has a lot of impact, primarily because this return is going to occur over the span of 10 to 15 years, and within this 10 to 15 years there will be different factors associated, like there will be interest rate will be there will be inflation will be there are some uncertainties associated with the market, and other things are there. So all these consideration need to be incorporated when we are calculating the detailed cash flows. Okay, so a key simple measure include a gross profit, net profit before taxes, net annual earnings, and return on investment. So these are the definitions which are given here. We are going to look at each of these a little bit in more detail. So gross profit is nothing but what? Gross sales minus manufacturing cost, that is the gross profit. Net profit before the sales is nothing but gross profit minus the expenses associated with the sales, administration, research and engineering, and that is represented as share. So share expenses, if we subtract from the gross profit, that gives us the net profit before the sales. And then the next is net annual earning. So net annual earning is nothing but net profit before taxes minus taxes on the net profit. So whatever the net profit we have obtained here, the same we can subtract, the taxes we can subtract from the same, and we can get the net annual earnings. So this simple calculations can give us whether the project is viable or not. While simple measures provide a quick snapshot of the profitability, clearly these calculations can give us whether the project is profitable or not, but they oversimplify the financial analysis and fail to capture the nuances of cash flow dynamics and investment risk. So how the different payments will be done over the period, so that cash flow and also the risk involved in the investment based on the fluctuation in the market, all these things are not included in these simple calculations. So some of these measures we can look at next. So when we are talking about the return on investment, okay, these are some of the definitions which we wanted to see here. So return on investment is calculated as net annual earnings divided by fixed and working capital. So whatever the net annual earning we are having, that divided by fixed and working capital, that gives us the return on investment. So typically a minimum desired return on investment is around 15%. So if it is less than, then it is not viable. Okay, so this is with respect to when we have deducted the taxes, but when we have not deducted the taxes, in that case it should be 30%. So 30% before the taxes. Okay, so return on in investment, return on investment doesn't consider the time value of the money. So you can see that here we are not looking at how the value of the money is going to change over the project duration. Okay, and is most suitable for mature planned projects with insignificant startup cost. So whenever there are insignificant startup costs are there, so you are not taking any loan from the bank, you don't have any financial commitments. So and the plant is reasonably matured, only in that case this return of investment makes sense. Okay, so the next definition here is a payout time. So this is determined by dividing total capital investment by net annual profit before taxes plus annual depreciation. So net annual profit before taxes plus annual depreciation, that we can sum up, and that if we divide the total capital investment by this net annual profit before taxes plus annual depreciation, that gives us the payout time. So what is payout time? So payout time basically represents time taken to recover the investment based on the net income. So whatever the net income a particular project is having, based on that how much time it will take to recover your investment. So again in this case you can see that we are not considering the depreciation. So this is without considering the depreciation. Again, like return of on investment, payout time doesn't account for the time value of the money. So it also doesn't account the time value of the money. The other two definitions are proceeds for dollar outlay. So proceeds for dollar outlay, which is represented as PDO, it is given as dividing the total net income over the project's life by the total investment. So total net income over the project's life, that we can sum up, divided by the total investment, that is going to give us the proceeds for the dollar outlay. Again, PDO doesn't include the depreciation and overlooks payment timing and project duration. The next definition here is annual proceeds per dollar outlay. So this is slightly extended from the PDO itself. So whatever PDO we are going to calculate, this PDO divided by the project life, if you do that, we are going to get the annual proceeds per dollar outlay. So that uh, so you can see that it is calculated by dividing PDO by project's life. So APDO shares the limitations of both measures and tends to favor short quick returns projects over the longer steady ones. So you can see that if we are making the decision based on the APDO, we are calculating what is the uh, uh, with respect to per year we are calculating. So you can see that in this case the shorter and the quick return projects will be favored over the longer and steady ones. Okay, the next definition here is average income on initial cost. So this is obtained by dividing the net profit before taxes including the depreciation by fixed and working capital. So like payout time, even if you look at the average income on initial cost, which is abbreviated as AIIC. So AIIC incorporates investment recovery as a cost but disregard the time value of the money. So you can see that all these definitions, all these terms which are used for uh, uh, analyze the financial viability of a project, in all these metrics you can see that the time value of the money is not used. Now let us take a very simple example to calculate all this, so that we understand this concept a little bit in more detail. So let's say we are provided with a economic information for a process with a capacity of 120 into 10 raised to power 6 kg per year, and the product price is around $0.3 per kg. The plant's financial details are given here. You can see the fixed capital cost is uh, 15 into 10 raised to power 6. Working capital is fixed working capital is 3 into 10 raised to power $6, and fixed and working capital will be nothing but what total of these two. So that will be 15 plus 3, that will be 18 into 10 raised to power $6. Then if you look at the raw material cost is around, let's say 0.08 dollars per kg of the product. So we can calculate. So the capacity of the plant is 120 into 10 raised to power 6, so that we can multiply to 0.08, we will get 9.6 into 10 raised to power 6 dollars per year. Again, the utilities cost here is 0.012 dollars per kg. So again, this $0.012 per kg of the production we can multiply by the total production. So total production will be again 120 into 10 raised to power 6, that we can multiply here. What we are going to get is 1.44 into 10 raised to power 6 dollars per year. And similarly we can calculate even the labor cost. So labor cost, again the rate is given here, which is 0.015 dollars per kg of production. So again we can multiply 120 into 10 raised to power 6 and we will get 1.8 into 10 raised to power 6 per year. So you can see that these the last three items, this actually part of the operating cost, isn't it? And in addition to this, there are some more factors which are associated with the operating cost. These are given here. So manufacturing cost is around 6% of the uh, fixed capital. So fixed capital we can obtain, which is given here is 15 into 10 raised to power 6. So we can multiply that to this 6% and we can obtain the manufacturing cost. So that is around 0.9 into 10 raised to power 6 dollars per year. Supplies 2% of the fixed capital. So fixed capital is again 15 into 10 raised to power 6 dollars. So that we can multiply here. We can get 0.3 into 10 raised to power 6 dollars per year. Depreciation rate we have taken 8% per year. So 8% per year we have taken the depreciation. So with this, the depreciation cost comes around 1.2 into 10 raised to power 6 per year. So then the taxes and insurance we are calculating, that is around 3% uh, uh, per year. So 3% per year, that comes around 0.45 into 10 raised to power 6 uh, per year. And we can add all these costs along with this. So you can see if we add these costs, it comes around 2.85 into 10 raised to power 6 per year, and this is around 12.84 into 10 raised to power 6 dollars per year. If I add both these, what we get is the total manufacturing cost. So total manufacturing cost comes around 15.69 into 10 raised to power 6. So this is nothing but what? This we have obtained by subbing this 12.84 into 10 raised to power 6 plus 2.85 into 10 raised to power 6. So that comes around 15.69. So once we have obtained the manufacturing cost, then now we can again obtain how much is the gross sales. So you can see that the rate is given. You can see that the product price is 0.3. So 0.3 multiplied by this 120 into 10 raised to power 6, that is going to give us the gross sales. So gross sales comes around 36 into 10 raised to power 6 dollars per year. Now gross profit will be what? Gross sales minus this cost, total manufacturing cost. So total manufacturing cost is 15.69 into 10 raised to power 6. If I subtract that from the gross sales, we get the gross profit. So which comes around 20.31 into 10 raised to power 6 dollars per year. And again from this gross profit we have to subtract the share expenses. Remember the share expenses which we have defined here. So share expenses are nothing but sales, administration, research and engineering expenses. So these expenses we can subtract. So if we take the share expenses as around 10% of the gross sales, then 10% of this 36 will 36 into 10 raised to power 6 per year, that becomes 3.6 into 10 raised to power 6 dollars per year. I can subtract that from the gross profit and that gives us the net profit before the sales. So net profit before the sales comes around 16.71 into 10 raised to power 6 per year. Now we can consider the taxes. Remember this net profit before sales is excluding the taxes, isn't it? So if we include the taxes, in that case the 50%, let's say the taxes are there. So taxes, if we take the 50%, then 16.71 into 10 raised to power 6 into 0.5, that will give us 8.355 into 10 raised to power 6 dollars per year. This will be the amount which has to be paid as a taxes. And if we can subtract these taxes from the net profit before the sales, we are going to get net profit after the taxes. Okay. So net profit after the taxes comes around 8.355 into 10 raised to power 6 dollars per year. This is the value we are getting. Now based on these values, now we wanted to calculate different metrics. So these are the different metrics, which is return on investment, payout time, PDO, APDO, AIIC, all these metrics which we have defined on the earlier slide, we are going to calculate here. So return on investment, you can see that return on investment we have defined as the net annual earning divided by the fixed and the working capital. So net annual earning we have obtained as, net annual earning is this 8.355 into 10 raised to power 6 divided by fixed and working capital. So that is 18 into 10 raised to power 6. So we are going to get 46.41. That is the percentage return on investment. Okay. So into 100, it should be into 100 here. So we will get 46.41%. Then payout time. Again, the payout time we have defined earlier. So payout time is nothing but what? Total capital investment divided by net annual profit before taxes plus annual depreciation. So you can see that in this case, so 18 into 10 raised to power 6 is the total capital investment, isn't it? 18 into 10 raised to power 6, that is the total capital investment divided by in this case the net net profit before the sales is 16.71 into 10 raised to power 6 plus depreciation. So depreciation values also we have calculated. So depreciation is 1.2 into 10 raised to power 6. If you include that here added, so with that the payout time comes around 1 year. Okay. Then PDO. So PDO which we have defined as proceeds for dollar outlay. So that we have defined as total net income over the project's life by the total investment. So whatever the total net income is there over the project's life divided by total investment, that is what the proceeds for dollar outlay. So in this case 16.71 is the net profit before the sales per year, isn't it? And remember in this case the depreciation is also there. So depreciation in this case the depreciation is 1.2 into 10 raised to power 6. So you can see that the depreciation amount we can claim the tax rebate on this. So we can add this as the numerator here. So 16.71 plus 1.2 into 10 raised to power 6 divided by multiplied by, if we take the total period of this entire project life of this particular project is, let's say, 12 years. So this entire thing multiplied by 12 and divided by the total capital investment. So total capital investment in this case is 18 into 10 raised to power 6. So we get PDO around 11.94. Now this PDO divided by the number of years, project years, so that is 12 years we have taken as a service life year. So you can see that the APDO we can obtain as 11.94 divided by 12, so that comes around 0.995. That is what the annual proceeds for dollar outlay, annual proceeds per dollar outlay, we get around 1.99 something. The next is the income on initial cost, AIIC. So you can see that AIIC is obtained by dividing the net profit before taxes including depreciation by fixed and working capital. So in this case AIIC is obtained as 16.71 is we have obtained the net profit before the sales divided by 18 into 10 raised to power 6. So that is nothing but the total capital cost, and the AIIC comes around 0.928. So these are the different metrics which we can calculate, and based on these metrics we can decide, at least preliminary decision we can make based on this, that whether a particular project is financially viable or not. However, you can see that all these metrics which we have seen so far, they do not include the time value of money, and you can see that the time value of money is very important when we are doing the cost calculations. So let us look at some details on time value of money. So basic economic measures provide provided earlier may not be sufficient for effective comparison because they do not include the time value of the money. So consideration for payment and income schedules are done by recognizing the fluctuations in the value of money due to various factors. You can see that the value of money can change because of different factors, and these factors are given here. So first factor is interest. So reflects the payment for using the money. So whatever 100 rupee I am using today, that 100 rupee is not 100 after 1 year, isn't it? So some interest will be there. Maybe let's say if I take the 10% interest, so in that case in the next year the value of that money becomes 110, isn't it? So interest can change the value of the money. Then the return from competing investment. So very often the plants invest in the competing investment, and based on that investment must offset the opportunity cost of the investing elsewhere. So based on that you will get some revenue. And the third one is the inflation. So because of the market fluctuation, the prices of the different commodities changes, and that can impact the value of money. Usually the inflation is also included in the interest rate itself. Okay, so this inflation part can also be taken into the consideration directly by having a different value of the interest rate itself. Okay, then the time value of money concept recognizes that a dollar received today is worth more than a dollar received in the future. So if I get 100 rupees after 1 year, there its value today will be lower. Okay, so due to potential earning capacity of the money over time, isn't it? So over the period the value of the money increases, and because of that whatever the 100 rupee I am having today, it will become a higher value after 1 year, isn't it? So if I am getting the revenues in future, their present value I need to calculate today in order to see whether a particular project is financially viable or not. So you can see that the time value of money is extremely important, because we are going to get the revenue over the project life of the plant, and over the this entire project life of the plant we are going to get uh, the returns from the plant. And if we look at the project value, time value of this recovery, then and then only we will be able to make the correct decisions in this case. So understanding the time value of money is crucial in economic evaluations, as it allows for the comparison of cash flows occurring at different points in time. Time value of the money analysis enables decision makers to evaluate the financial attractiveness of the projects, accounts for the inflation, and make informed investment decisions. Again, comparing the cost and benefits over the different time periods required adjusting cash flows to a common time basis using discounting or compounding techniques. So this we will see. If we are trying to calculate the cost today based on the revenues which we are going to get in future, in that case we have to look at the discounting factor. And if we are looking at how the earning is going to impact in future, in that case we have to look at the compounding factor. Okay, so both these things we are going to look at little bit in detail in the subsequent slides. Okay, now let's look at the time value of money. So initial step in the economic analysis involves understanding the impact of compounded interest rates. So in this context we define P as the present value of the sum and S as the future worth. So compounding interest after 1 year period is expressed as. So you can see that, let's say if I am having P amount today, what will be its worth after 1 year, that we are calculating using this equation. So S is nothing but the value of this money after 1 year. So S will be given as P into 1 plus I, where I is the interest rate. Now this is the uh, uh, how the value of the money is going to change over the period, that is accounted using this equation. Now let's say if you are looking at the compounding of the interest rate annually, and we are looking at the time value of money over the multiple years, in that case the S is given as P into 1 plus I raised to the power n, where I is the annual interest rate. So this formula illustrates that the investment of, if let's say if we invest $1,000 with let's say 10% interest rate, then after 1 year we are going to have $1,100. Okay, again the present value of the future sum can be determined using the formula. So whatever the return we are getting in the future, if you wanted to see what will be its present value, in that case we can get P as S divided by 1 plus I raised to the power n. So with this particular formula we can calculate the present value of the amount which we are going to get in the future. So here 1 upon 1 plus I raised to the power n, this particular factor we call as discount factor. Remember in the last slide we said discounting factor. So this particular factor is nothing but the discounting factor. So 1 divided by 1 plus I raised to the power n, this is a discounting factor. So again, let's take a simple example. Let's say if you are having $106 in 100 years with compound interest of, let's say, 0.05%, we wanted to find out the present value of the principal. So we can find out the present value of the principal directly by using this equation. So 106 we are going to get after 100 years, isn't it? So 106 divided by 1 plus I raised to the power 100, because the number of years here are 100. I is, let's say, if you take 0.05, in that case the value of P is $0.8. So you can see that if I invest $0.8 today, after 100 years its value will be 106 with the interest rate of 0.05. Similarly, if I take an interest rate of 0.2, so in this case interest rate is lower, but let's say interest rate is higher. In that case you can see that even if I am investing a very small amount today, it's going to become 106. So you can see that in that case this principal amount comes out to be 1.2799 into 10 raised to power 6. Okay, very small amount. If we invest today, we can get 106 after 100 years. So you can see that the time value of the money has impact on the cost calculation. So let's look at the different compounding and the effective interest rates here. So the formulas for the principal and S discussed earlier are applicable when the compounding period matches the nominal rate per period, typically on an annual basis. So whenever we are having the compound interest rate given in an annual basis and it is getting accrued annually. However, if interest rates are compounded multiple times within a year, let's say it is compounded multiple times within a year, the effective rate can slightly change or it exceeds and the nominal rate. So this is demonstrated by the following parameters. Okay, you can see that this is the example here. So nominal interest rate is, let's say, I, number of periods for the nominal rate is n, and the number of compounding intervals per nominal period is, let's say, m. And in this particular case, the earlier formula which we have seen, this earlier formula which we have seen, this is going to get modified when we are having uh, multiple compounding cycles per year. In that case we can get S as equals to P into 1 plus I divided by m raised to the power mn. Here you can see that if I am having the interest rate given and it is getting accrued annually, in that case it is just 1 plus I raised to the power n. But let's say the interest is getting compounded multiple times over a year. In that case it becomes 1 plus I divided by m. Here m is how many number of times the compounding is taking place per year. So I divided by m raised to the power mn. So take an example here. Let's say a nominal interest rate is, let's say, 6%. And let's say if you are saying that this interest is getting compounded 4 times within a year, let's say n is equals to 1 year, we can calculate uh, the the interest rate here. In this case the discounting factor will be what, the accounting factor will be what, 1 plus 0.06 by 4 raised to the power 4. So this comes around 1.0614. So you can see that actual interest rate was 6%, but because of compounding 4 times a year, you can see that this interest rate is actually increased to 6.14. So it's not 6. So you can see that more number of compounding you are performing in a given nominal period, your interest rate is going to increase. And let's say if we say that there is a continuous compounding taking place, if we take the infinite number of compounding intervals, we approach to a limit for the effective interest rate. So if we are having, let's say, this compounding is taking place continuously, the and in that case the same formula which we had looked at earlier, this the same formula we can modify. So in this case, what will be the formula will be nothing but what, here m will be infinite, because number of compounding you are performing infinite number of times. So s is given as limit m tends to infinity. Here the same equation is there, uh, 1 plus I divided by m raised to the power mn. Here m tends to infinity. If we solve this limit, what we get is p into e raised to the power in. So we can calculate the interest rate, or we can calculate what will be the value of the money if there is a continuous compounding taking place. Now this concept is useful where, this concept is extremely useful whenever we are having the continuous payments or revenues occurring. Okay, continuously payments are coming, or revenues are coming. In such cases, uh, this continuous interest is important. So as the process continually generates the income over the or incurs the expenses, determining the effective rate becomes pertinent. So you can see that in such cases, the what will be the effective interest rate? Effective interest rate in this case will be EIN minus 1. That will be the effective interest rate, and this effective interest rate will be higher than the nominal interest rate. So you can see that if I take the 6% nominal interest rate, the effective interest rate comes out to be 6.18. You can see that it is increased. The next is the annuities. So this particular concept is useful to determine the present value of the distributing equal payments regularly. We assume that these payments occur at the end of the each period. So this happens whenever the company or organization has taken a loan, uh, or if the organization need to pay the insurance premiums. So these are paid in a yearly manner, isn't it? So we can calculate the discount factor for such payments. So you can see that the p can be calculated as r divided by uh, 1 plus I. uh, this is for the year 1. For second year it will be r divided by 1 plus I raised to the power 2, and this summation goes all the way to the entire period of the project. So in a way, p is given as r into summation of 1 upon 1 plus I raised to the power k, where uh, the k is varying between 1 to n. So you can see that in this particular manner we can calculate the present value of the money when we are getting the cost associated every year with respect to the life insurance premiums or the loan premiums. Okay, and we will see one example on this to understand this concept little bit in more detail. Now let's look at some more concepts, and then we will go back to the example. So there is something called as depreciation. Now this depreciation is very important, particularly for the cost calculation purpose. Okay, so depreciation is a method used to allocate the cost of a tangible assets over its useful life for accounting and tax purposes. You can see that the depreciation serves as a tax incentive. This is very important. So you can calculate the depreciation, and you can use that as an incentive by reducing the taxable income, thereby lowering the amount of taxes a company owes. So company employed depreciation techniques are shaped by consideration of precision, ease of use, and financial advantage, and are naturally subject to regulatory guidelines set by the tax authorities. So in what way you should calculate the depreciation is set guidelines are given by the regulators, and based on that the depreciation should be calculated. So there are two types of depreciation calculations. The first one is the straight line calculation. So in this method entails uniform depreciation write-offs over the project lifespan, offering simplicity in calculation. So what we are doing is we are finding out the depreciation in a linear manner. Okay, so straight line uh, depreciation we are assuming here. There is another depreciation calculation which is a declining balance. So in this case what we are doing is, this approach involves accelerated depreciation with larger write-offs occurring earlier in the project life. So accelerated depreciation means, So you can see that here there is no the linear depreciation occurring, but in this case the larger write-offs are occurring earlier in the project life. Okay. So again, which method is suitable, which method is approved by the regulatory authorities, based on that the depreciation should be calculated. So choice of depreciation method can influence the company's financial statements, tax obligations and overall profitability. Tax laws and regulations govern the depreciation method allowed for tax purposes, ensuring the consistency and compliance across the businesses. Okay. So the next important concept which we have to look at is the inflation, which also have the significant impact on the cost calculation of the company. So inflation refers to the general increase in prices of goods and services over time, leading to a decrease in the purchasing power of the money. Okay. So the inflation rate represents the percentage change in the price level from one period to another, typically expressed on an annual basis. Inflation affects both cost and revenues, influencing the project economics, investment decisions, and financial planning. Adjusting for the inflation involves incorporating the expected rate of price increase into cash flows, projections, and financial calculations. Okay. So here what we are trying to say. So see, because of inflation, what will happen is the cost of different goods are going to increase over the period, and this inflation we have to consider while making the decision in the starting itself. So the good idea is to include the inflation in the cost calculation, and based on that we can see whether the particular project is financially viable or not. So you can see that adjusting for the inflation involves incorporating the expected rate of price increase into the cash flow projections and financial calculation in the future. Okay. Again, the present value analysis. So now how we can account the inflation? So we can account the inflation in the present value of the money. How? By modifying the interest rate. So by modifying the interest rate, we can account the inflation similar to the time value of the money, isn't it? So in a similar manner, we can account the impact of the inflation also um, uh, by calculating the present value of the money. Okay. So present value analysis with inflation requires discounting future cash flows at a rate that accounts for both time value of money as well as expected inflation rate. Accurately forecasting inflation rates and incorporating them into financial models can enhance decision making and risk management strategies. So clearly, if you include the inflation, you are trying to mitigate the risk which are going to happen in the future based on the market volatility or the increase in the prices of the goods. Okay. So the next important aspect is the investment risk. So investment risk refers to the uncertainty or potential for financial loss associated with an investment decision. Various factors contribute to investment risk. This includes market volatility, economic conditions, regulatory changes, competition, and project specific risks. So all these risk factors one has to evaluate in order to see whether a particular project is viable or not. So quantifying investment risk involves evaluating the likelihood and impact of various risk factors on project performance and financial outcomes. When faced with the risk in decision making, it is important to explore potential alternative outcomes and evaluate them similarly to risk free scenarios. Okay. So you can see that while making the decision, when there are multiple alternatives are there, if you are making the decision based on the risk associated with the project, you can get the multiple choices, and then you can select a particular choice based on how much risk company is willing to take. Okay. So unfavorable outcomes from the previous decisions are likely to impact the subsequent decisions, necessitating the establishment of the protocols for managing such situations. Each decision alternative presents a spectrum of potential outcomes with associated probabilities, allowing for the assessment of the expected values to inform decision making. Okay, so you can see that with respect to different risk factors, there is a probability associated, isn't it? So all these probabilities one can assess, and then one can make the decisions intelligently. So simply conducting cash flow analysis is insufficient. Clearly, only based on the cash flows, if you are making the decision, that is not sufficient, primarily because how the market is going to behave in future, how uh, the regulatory bodies are going to change their rules. All these factors are important, isn't it? A common example is now you can see that the government is trying to put uh, the carbon reduction on the CO2 exerted in the environment. So this type of policies can have the impact, isn't it? So one has to account such regulatory compliances, also the volatility in the market. Okay. So in conservative scenarios, the focus may be on selecting the best possible outcome among unfavorable options with a significant probability of occurrence. The willingness to take risk is influenced by the prevailing economic conditions. So what is the economic condition, whether it is good? If the economic condition is good, in that case you are more optimistic for taking calculated risk, whereas when the economic uncertainty is there, in that case you try to become more conservative in making the decisions. So now we will see one example based on the cost calculations and how the time value of the money is important while making the decisions. So in this particular example, we are trying to find out the optimum value of the insulation thickness. So you can see that there is a pipe is there. So this is, you can consider that these are nothing but the steam carrying pipe, and you can see that the more the insulation you put, more the heat loss you are going to save, and based on that the loss to the company will be reduced. But as you increase the amount of insulation, the cost of the insulation is also going to increase, isn't it? And again you can see that the loss of this heat loss is going to occur over the entire lifespan of the insulation, isn't it? So you can see that you are going to get you are going to get the return back over the period, isn't it? It's not immediately, isn't it? So time value of the money is also important here. So heat loss is reduced, the cost of the energy lost is decreased. So again the higher is the cost of insulation. So you can see that as the increase in the insulation above the critical thickness, the heat loss is reduced, and because of that the cost of the energy lost is decreased, whereas the insulation cost increases. So there is a trade-off between these two. So economic or optimum insulation thickness is that for which the sum of the insulation cost and the cost of the heat loss is minimum. So we will be adding both these costs, cost with respect to the energy loss and cost incurred because of the insulation, and the total cost then we are going to minimize, and we wanted to find out what will be the optimum value of the insulation thickness, which is going to give us the minimum value of the cost. So the factors here are the fixed cost of insulation. There is a variable cost like maintenance cost is there. So this we have neglected. Service life of the insulation, depreciation and taxes are there. So all these are the factors associated. Now in this case, in this particular case, the hot steam is flowing through this pipe. So you can see that the H naught is the film coefficient at the outer surface. So outside here there is a film coefficient which is given as H naught. Then thermal conductivity is kilocalorie, given K is the thermal conductivity which is given as kilocalorie per hour per meter per degree Celsius. So C is the cost of insulation which is given as rupees uh, per meter cube, and the CH is the cost factor of the energy which is given as rupees per kilocalorie. Here I is the interest rate, annual interest rate, N is the insulation life, and T naught is the ambient temperature, and Ti is the pipe wall temperature. Okay. Now based on this information, we wanted to develop the cost equation here. So in this case, you can see that the inside heat transfer coefficient Hi we are assuming to be large. So you can see that inside the pipe the steam is flowing. So inside heat transfer coefficient we are assuming very large. So clearly the rate limiting heat transfer coefficient is the outside heat transfer coefficient and the conduction resistance offered by the pipe wall. So you can see that this conduction resistance offered by this pipe wall and the resistance because of the film happening outside of this particular pipe, these are the two prominent resistances we are including in the heat loss. So overall heat transfer coefficient is calculated based on these two rate limiting factors. So you can see that the UI, which is nothing but the overall heat transfer coefficient calculated based on the inside surface area, which is given as 1 upon Ri ln R naught by Ri by K plus Ri by H naught into R naught. So here you can see that Ri is the inside radius of this particular pipe. R naught is the outside radius of the pipe after applying the insulation. T naught is the outside ambient temperature, H naught is the outside heat transfer coefficient, K is the thermal conductivity, Ti is the inside temperature. So now with this, Ui is calculated using this particular formula, and the heat loss will be given by what? Heat loss in this case will be given by UA delta T, isn't it? So in this case, U is this, A will be 2 pi RIL. So this is area, heat transfer area, which is nothing but this outside circumferential area. This outside circumferential area of this particular tube is the total heat transfer area, into temperature difference, which is nothing but Ti minus T naught. So now we wanted to calculate this heat loss over the year. So if we assume that 300 working days and 24 hours are there, so that becomes UA delta T into 24 into 300, so that gives the heat loss per year. So cost of the heat loss will be given by QCH. So in this case, this Q, if we multiply it by a cost factor, we get the cost of the heat loss in rupees per year. And remember, in this case, this cost of the heat loss is going to occur over the time span, over the period, isn't it? So in this case, let's say there are n years are there. So n year is the lifetime of the insulation in that case. And if you take the I as a fractional annual compound interest rate, in that case the present value of this cost will be given by QCH divided by 1 plus I raised to the power j. So you can see that this equation is same as the equation which we have seen earlier, isn't it? So we are calculating the present value of the future cost. So this present value P1 we have calculated. Now similar to this cost of the heat loss, there is a cost associated with the insulation. So you can see that in this case the cost of the insulation is given per meter cube. So we have to calculate the volume of the insulation required. So you can see that the volume of the insulation required will be what? Pi R naught square minus Ri square. That will be the amount of insulation, the volume of the insulation required, because in this case you can see that the insulation will be this, and we are taking the negligible thickness of the pipe wall. So in this case you can see that the thickness of the insulation will be what? R naught minus Ri, isn't it? So volume of the insulation will be R naught square minus Ri square into pi, that is the area, multiplied by L, length. So that gives us the volume of the insulation required. Now if I multiply this particular equation to a cost factor, that gives us the present value of the insulation. Since the insulation cost we have to pay in the current year itself, so in this case the present value of the insulation will be pi into R naught square minus Ri square into Lc. The present value of the insulation, total present value of the cost will be P1 plus P2. So this P1 we have calculated here, plus this P2, which is the insulation cost. So this total we have taken here. Now here the Q we can replace by this particular equation, where Ui is again we can replace by the original equation here. So with that, the total present value Pt is given as Ch in the bracket summation j equals to 1 to n 1 upon 1 plus I raised to the power j. So this is nothing but the discounting factor multiplied by 2 pi RIL. This is nothing but the circumferential area, heat transfer area, into U. The equation of U is given as 1 upon Ri ln R naught by Ri divided by K plus Ri by H naught R naught into delta T. So that is Ti minus T naught into 24 into 300 plus pi R naught square minus Ri square into Lc. Now this is the entire equation which we have obtained, and we wanted to find out the optimum value of the Pt. We wanted to find out the minimum value of the Pt, and we are interested in finding out what value of the insulation thickness is going to give us the minimum value of the Pt. So you can see that in this particular equation Ri is a fixed, whereas R naught is a variable. So we can differentiate this equation with respect to R naught, and we can equate that to 0, and it is going to give us the optimum value of R naught, and optimum value of R naught minus Ri, that is going to give us the optimum value of the insulation thickness which is required for minimizing the cost. So if you look at P1, you can see that as the insulation thickness increases, the P1 decreases. P1 decreases because the heat loss to the ambient decreases, and because of that P1 is going to decrease as R0 minus Ri increases. But you can see that as R0 minus Ri increases, you can see that the insulation cost increases. So you can see that if we consider both these costs P1 and P2, there is a point somewhere here when their sum is minimum. So this particular point actually represents the optimum value of the insulation thickness. So we can obtain we can apply the insulation value with this optimal thickness, which is going to minimize the cost required for the insulation and its return. Okay, so this is all about the cost calculation. Thank you. We are going to continue with the batch plans in the next session.